For as long as humanity has existed, we've looked up at the night sky and asked the same timeless question: what else is out there? Beyond our small world lies a universe almost impossible to comprehend, a cosmos stretching across billions of light years, containing hundreds of billions of galaxies, each filled with billions of stars and countless worlds waiting to be discovered. Within this immense cosmic ocean are planets unlike anything we could ever imagine, mysterious objects that challenge the very laws of physics, and forces so unimaginably powerful that they can bend space and time, tear apart stars, and reshape entire galaxies. In this marathon, we'll journey across the observable universe to explore what real alien life might actually look like, why we've never found evidence of extraterrestrial civilizations, the strangest planets ever discovered, the terrifying reality of black holes, and the most violent events known to science. Every chapter brings us closer to understanding just how extraordinary and how humbling our universe truly is. This is the Observable Universe Phase 1 Cosmic Wonders. Let's begin our journey. Right now, Earth is the only confirmed example of life in the universe. That means every prediction we make about aliens starts with one dataset: biology on this planet. Life here is built on carbon chemistry, liquid water, DNA-based evolution, and energy extraction from environments. So when scientists look for alien life, they don't start with imagination, they start with constraints. Physics first, biology second. To imagine alien life, we first need to ask, where could it actually survive? Astronomers now know that there are billions of planets in just our galaxy alone. Many of them are exoplanets, planets outside our solar system. Some are rocky, like Earth, and some orbit in the habitable zone, where liquid water could exist. That's key. Not because water is magical, but because it's an excellent solvent for chemistry. It allows molecules to move, collide, and form complex structures. But even within the habitable zone, conditions vary wildly. Some planets might have thick atmospheres like Venus, others might be frozen like Mars, some could have stronger gravity or weaker magnetic fields. So any alien life would already be shaped by extreme environmental pressure. On Earth, evolution is not random chaos. It follows a few major rules, and these rules would likely apply to alien life too. First, survival favors efficiency. Evolution doesn't create perfect organisms, it creates organisms that waste the least energy while surviving long enough to reproduce. You can actually see this on Earth everywhere. Birds evolved hollow bones for lighter flight. Deep sea creatures move slowly because food is scarce. Everything in nature is constantly balancing survival against energy cost. And that leads into the second rule. Energy use is everything. Every living thing needs energy to move, grow, hunt, think, and survive. Even human intelligence is extremely expensive biologically. Our brains use a massive amount of energy compared to the rest of our bodies. So intelligence only evolves if it's actually worth the cost. On another planet, evolution might favour something completely different. Maybe creatures become incredibly efficient instead of intelligent. Maybe life remains simple for billions of years because simplicity works. The third rule is that adaptation depends entirely on environment. Life changes based on the conditions around it. Desert animals conserve water, deep sea creatures handle pressure, cave animals sometimes lose their eyesight completely because vision becomes useless in darkness. So on alien planets, different environments could create life forms that seem bizarre to us, but make perfect sense for their own world. And finally, random mutation and natural selection drive complexity. Small random genetic changes happen constantly. Most do nothing, some are harmful, but occasionally one gives an organism an advantage. Over millions of years, those tiny advantages stack together and create incredibly complex life. That means alien life probably wouldn't look designed. It would look evolved, shaped slowly by survival, environment, and time. So if life exists elsewhere, evolution will still work the same way. That's important. It means aliens aren't designed, they're shaped. So instead of asking, what would aliens look like? Scientists ask, what body plan would be most efficient in that environment? Let's imagine a rocky planet slightly larger than Earth. Higher gravity means shorter, stronger organisms are favoured, tall creatures become structurally inefficient, and movement requires more energy. So instead of humanoid giants walking upright, you might get low-profile, ground-hugging organisms, wide, stable body structures, and possibly even multi-limbed crawler forms. Now imagine the opposite, a low-gravity planet. There, evolution could favour taller organisms, floating or gliding motion, and more fragile but expansive structures. So even before thinking about intelligence, gravity alone completely reshapes biology. On Earth, we rely heavily on vision, but that's not guaranteed elsewhere. On a planet with thick fog-like atmosphere, vision becomes useless. Dense oceans, sound and pressure become more important. Weak light from a red dwarf star, infrared sensing might dominate, so alien senses could be radically different. Echolocation like bats or dolphins, electromagnetic field detection like some fish, chemical smell mapping over long distances could even be possible. An alien might not see you at all, but it might feel your presence through environmental changes. One of the biggest assumptions we make is that intelligence leads to a humanoid shape, but evolution doesn't care about symmetry or aesthetics, only function. On Earth, intelligence evolved multiple times. Primates, dolphins, corvids like crows and ravens, and even octopuses. Notice something important. None of them look even remotely similar. In fact, octopuses are especially interesting because their intelligence involved a completely different body structure. Distributed brains, flexible limbs, and problem-solving ability without a central human-like brain. So alien intelligence could be distributed across a colony or organism. It could be hive-based like insects but far more advanced, or even planet scale, a networked biosphere acting as a single system. Carbon is the best known building block for life because it forms stable, complex chains, but other possibilities exist, like silicon-based chemistry, less flexible but still possible in theory, or alternative solvents like methane or ammonia in extreme environments. However, scientists still consider carbon-based life the most likely because it's extremely versatile, it works across a wide temperature range, and it's abundant in the universe. So even alien life might still be carbon-based, just not Earth-shaped. Now this is where things get interesting. Not all life has to be large or even visible. On Earth, most life is microscopic. Bacteria, archaea, microbial ecosystems under ice or rock. So statistically, if life exists elsewhere, it may also mostly be microscopic. That means the most common alien life in the universe might be invisible, simple, and widespread. Not spaceships or civilizations, but microbial ecosystems under alien oceans or buried beneath rock. Now here's a difficult question. If alien life is too different, would we even know it's alive? This is one of the major challenges in astrobiology and SETI research, the search for extraterrestrial intelligence. SETI Institute works on detecting signals that might indicate intelligent civilizations, but even that assumes intelligence uses detectable communication. Life elsewhere might not emit radio stations, build technology, or even behave in ways we classify as life. It could exist in forms we mistake for geology or chemistry. So after all of this, what's the most scientifically realistic alien? Not a humanoid, not a monster, not something designed for storytelling. The most realistic alien is probably simple or microbial, adapted perfectly to extreme conditions, chemically familiar but structurally unfamiliar, driven entirely by evolution, not intelligence or intention. And if complex aliens do exist, they are likely so shaped by their environment that they would feel less like characters and more like entirely separate branches of biology. When we imagine aliens, we usually imagine them as variations of ourselves, but science suggests something very different. If life exists elsewhere in the universe, it won't be designed around human expectations. It'll be designed around physics, chemistry, and survival over billions of years. And that means the universe may be full of life, but almost none of it would look like anything we could easily recognize. Which leads to a final thought. The real mystery isn't just whether aliens exist, it's whether we're even capable of recognizing them when we find them. The scale of the universe is almost impossible for the human brain to truly understand. Light itself travels at nearly 300 million meters per second, fast enough to circle Earth more than 7 times in a single second, and yet even at that speed, light from our nearest neighbouring star still takes over 4 years to reach us. The Milky Way galaxy alone is around 100,000 to 120,000 light years across, containing hundreds of billions of stars, and our galaxy is just one among trillions. When you look at the night sky, you are looking at a universe so enormous that intelligent life should statistically exist countless times over. Even if life is incredibly rare, the sheer number of planets should make alien civilizations almost inevitable. This mystery became known as the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Because when scientists began calculating the scale and age of the universe, the silence stopped making sense. Our solar system formed relatively late in cosmic history, which means there are planets out there billions of years older than Earth. If intelligent life emerged on just a tiny fraction of those worlds, some civilizations should already be millions of years ahead of humanity. And if civilization became advanced enough to travel between stars, it could theoretically spread across the galaxy in a relatively short amount of cosmic time. So if intelligent life is possible, why do we see absolutely nothing? To understand why this question is so unsettling, we only need to look at ourselves. Human civilization advanced from primitive farming societies to modern cities in only a few thousand years. In just over 100 years, humanity went from the first airplane to landing on the moon. Technology evolves extremely quickly, especially once a civilization begins developing computers, automation, and artificial intelligence. So imagine a civilization with even a small head start over humanity. Not 100 years ahead, not 1,000 years ahead, but 1 million years ahead. Their technology could be completely beyond our understanding. They may have mastered interstellar travel, built structures around entire stars, or spread across huge regions of the galaxy, and yet the universe remains silent. One possible explanation is that intelligent life is extraordinarily rare. Perhaps simple microbial life exists throughout the universe, maybe bacterial and primitive organisms are common, but the leap from simple life to intelligent civilization may be unbelievably unlikely. Life on Earth survived asteroid impacts, volcanic catastrophes, ice ages, and multiple mass extinctions. For billions of years, evolution continued through chaos after chaos. And despite all of that, human-level intelligence seems to have only appeared once. Earth may have experienced such an absurdly unlikely chain of events that intelligent life almost never emerges elsewhere. But there may be an even darker explanation, something known as the Great Filter. The Great Filter is the idea that somewhere between dead matter and advanced civilization, there exists a barrier, a stage that almost no life successfully passes. Maybe life itself is extremely difficult to begin, maybe complex cells almost never form, or perhaps civilizations destroy themselves soon after becoming technologically advanced. A species may survive for millions of years biologically, only to wipe itself out shortly after inventing powerful technology. Nuclear war, artificial intelligence, climate collapse, engineered pandemics, civilizations may repeatedly reach a certain point and then disappear. One of the most disturbing ideas is known as the dark forest theory. The theory suggests that the universe is silent on purpose. Imagine walking through a dark forest at night. You hear movement in the distance, but nobody speaks. Nobody reveals their location, because making noise could attract something dangerous. Now imagine the universe as that forest, filled with civilizations that remain hidden out of fear. An advanced civilization may see every unknown species as a potential threat. And in a universe where survival matters above all else, remaining silent may be the safest option. Of course, there are less terrifying explanations too. Space itself may simply be too enormous. Even travelling at the speed of light, journeys between stars would still take years. Travel across the galaxy could take millions. Civilizations may rise and fall before ever overlapping with one another. Two intelligent species could exist thousands of light years apart, separated not just by distance but time itself. Humanity has only been using radio technology for around 100 years, which means our detectable signals have travelled only a tiny distance into the galaxy. From the universe's perspective, we have barely begun announcing our existence. There is another possibility. Maybe humanity is among the first intelligent civilizations to emerge. The universe is ancient, but many stars in the early universe may not have contained enough heavy elements to form Earth-like planets. Complex life may require very specific conditions. Perhaps the universe needed billions of years before intelligent life became truly possible. And if that's true, then humanity may exist near the beginning of a much larger future cosmic story. The future where civilizations eventually spread across the stars, and perhaps one day we may become the civilization another species searches for. But regardless of the explanation, the silence of the universe changes the way we see ourselves, because either intelligent life is unbelievably rare, or the cosmos is filled with civilizations hiding quietly in the dark. Both possibilities are equally unsettling, and somewhere out there, across billions of distant stars, another civilization may be staring into their own night sky, wondering if they are alone, asking the exact same question we are: where is everybody? HD 189733b is one of the most famous exoplanets ever discovered. At first glance, it appears beautiful. Astronomers believe the planet would look deep blue from space, almost like Earth, but that colour is horrifyingly deceptive. HD 189733b is a hot Jupiter, a giant gas planet orbiting extremely close to its star. Temperatures reach over 1000 degrees Celsius, and the atmosphere likely contains vaporized silicate particles, essentially glass. Powerful winds whip through the atmosphere at speeds exceeding 8,000 kilometers per hour. That means the glass doesn't simply fall downwards like rain on Earth. It blasts sideways across the planet in a superheated storm of razor-sharp particles. The entire world is violently hostile. No surface, no oceans, no life. Just crushing heat and sideways glass storms under an alien blue sky. 55 Cancri E may be one of the most valuable planets in existence. This super-Earth is roughly twice the size of Earth and orbits incredibly close to its parent star. A year there lasts only about 18 Earth hours. Temperatures on the surface are hot enough to melt many metals. But what truly makes this planet extraordinary is its chemistry. Early observations suggest the planet may contain enormous amounts of carbon under immense pressure. If true, much of the planet's interior could exist in diamond form. Not tiny crystals, but vast planetary-scale layers of diamond. Entire mountain ranges may glitter beneath oceans of lava. Although later studies suggest the composition may be more complex than originally thought, the possibility of carbon-rich worlds remains scientifically plausible. which means planets fundamentally different from Earth may be common throughout the galaxy. WASP-12b is dying. This giant gas planet orbits so close to its star that gravity itself is tearing the planet apart. The star's tidal forces stretch WASP-12b into an egg-like shape. Its atmosphere has expanded far beyond the planet's normal boundaries, and now the star is actively pulling material away from the planet. Astronomers believe WASP-12b is slowly spiraling inward towards destruction. Eventually, the planet may be completely consumed. The temperatures here exceed 2,500 degrees Celsius. That's hot enough for some metals to exist as gas. Iron, magnesium, even exotic atmospheric chemistry that would be impossible on Earth. This is not a stable world. It's a planet caught in the final stages of a cosmic death spiral. PSR B1257 plus 12b was among the first confirmed exoplanets ever discovered, and it orbits something terrifying, a pulsar. Pulsars are the collapsed remnants of exploded stars. After a massive star dies in a supernova, its core can collapse into an ultra-dense neutron star. These objects spin rapidly while blasting intense radiation beams into space. The environment around a pulsar is unbelievably violent. Radiation levels would be catastrophic, yet somehow planets exist there. Any nearby life would almost certainly be destroyed by the pulsar's energy output, but the existence of these planets proved something revolutionary. Planetary systems can survive events far more catastrophic than scientists once imagined. Even the death of a star does not always destroy every world around it. TRES-2b is darker than coal, darker than black acrylic paint. It reflects less than 1% of the light that reaches it, making it one of the darkest known planets in the universe. Scientists believe the atmosphere may contain vaporized sodium, potassium, or titanium oxide that absorbs incoming light extremely efficiently. The planet is also incredibly hot, over 1000 degrees Celsius, so despite being nearly pitch black, it may glow faintly red from its own heat. Imagine standing near a planet so dark it almost disappears against space itself, only a dim crimson glow revealing its presence. It would look less like a planet and more like a hole cut into reality. J1407b may possess the largest ring system ever discovered, and it makes Saturn's rings look tiny. The ring system surrounding this object could span tens of millions of kilometers, so enormous that if it replaced Saturn in our solar system, the rings would appear vastly larger than the moon in Earth's sky. Astronomers detected this system when the planet passed in front of its star. The rings blocked enormous amounts of light in highly complex patterns. Scientists think moons may actually be forming inside the rings right now. In a sense, we may be witnessing the creation of an entire miniature planetary system. It's one of the clearest reminders that planetary systems are not static. They evolve, they collide, they grow, and sometimes they create structures almost beyond our imagination. Kepler-16b became famous for one incredible reason. It orbits two stars, a real-life version of the twin sunset world from the movie Star Wars. This type of world is called a circumbinary planet. Instead of orbiting a single star like Earth, the planet circles both stars together. From the surface, the sky would constantly change. Sometimes one sun would dominate the sky, sometimes both would appear at once, and the gravitational interactions make these systems extremely complex. For a long time, scientists weren't even sure stable planetary orbits like this were possible, but Kepler-16b proved they are real. The universe often produces systems stranger than science fiction imagined. TOI 849b may be the naked core of a failed giant planet. Normally, planets of this size become gas giants like Jupiter or Saturn, but TOI 849b is different. It appears incredibly dense, too dense to be mostly gas. Scientists think this world may once have been a giant planet surrounded by thick layers of hydrogen and helium, but somehow those outer layers were stripped away, possibly by stellar radiation, possibly through violent collisions, leaving only the massive core behind. If that idea is correct, astronomers may essentially be looking directly into the interior remains of a giant planet, something previously thought impossible. Gliese 436b contains one of the strangest substances in the universe, hot ice. The planet is extremely close to its star, temperatures are far above the boiling point of water. Yet scientists believe water may exist there in exotic high-pressure forms. Why doesn't it evaporate? Because the planet's gravity is enormous. The pressure becomes so intense that the water molecules are compressed into unusual states that remain solid despite the extreme heat. This is completely unlike ice on Earth. Not snow, not glaciers, but dense, superheated, crystalline forms of water under crushing planetary pressure, a reminder that even familiar substances can behave in alien ways elsewhere in the cosmos. HAT P67b is one of the least dense planets ever discovered. It's enormous, much larger than Jupiter, yet incredibly light. Its atmosphere is so expanded and diffused that the planet has been compared to cotton candy. If you could somehow place it in a giant ocean large enough to hold it, theoretically it could float. The planet's low density is likely caused by intense heating from its nearby star. That energy causes the atmosphere to swell outward dramatically. Worlds like this challenge our understanding of how planets form and survive. Because according to many older models of planetary formation, a planet this large and this light should barely be possible. For most of human history, the only planets we knew were the ones orbiting our own sun. Now we know the galaxy is filled with worlds beyond imagination. Frozen giants, burning oceans, dead stars surrounded by planets, worlds darker than charcoal, and planets where the laws of everyday experience completely break down. The universe is under no obligation to resemble Earth, and every new telescope reveals that reality is far stranger than we expected. Somewhere out there are almost certainly planets even more bizarre than the ones we've discovered so far. Worlds we haven't imagined yet, and perhaps one day humanity will finally see them up close. Until then, we can only look into the darkness and wonder what else is waiting out there. Imagine a black hole floating alone in space. At first, it might not look like much. You wouldn't see a giant cosmic vacuum cleaner pulling everything towards it. In fact, if the sun were magically replaced by a black hole of equal mass, Earth would continue orbiting almost exactly as it does today. Black holes don't pull harder simply because they're black holes. Their gravity depends on their mass. The difference is that all of that mass has been compressed into an incredibly small region. As you move closer, however, the black hole begins to reveal itself. Light from distant stars becomes distorted. The background universe appears warped. The black hole acts like a gravitational lens, bending the paths of light around it. The closer you get, the more distorted reality becomes. As gravity grows stronger, time itself begins behaving differently. According to Einstein's general theory of relativity, gravity is not a force in the traditional sense. Instead, massive objects curve space-time. One consequence of this curvature is gravitational time dilation. Clocks deeper in a gravitational field run more slowly compared to clocks further away. You wouldn't notice anything unusual about your own clock. Your heartbeat would feel normal, your thoughts would feel normal, but someone watching from far away would see your time slowing down. The closer you move towards the black hole, the greater this effect becomes. Near the event horizon, the difference becomes extraordinary. The event horizon is often imagined as a physical surface. It isn't. There is no wall, no gate, no sudden flash of light. If the black hole is large enough, you could cross the event horizon without immediately noticing anything special. From your perspective, nothing dramatic happens at that exact moment, yet crossing the event horizon changes your fate forever. Outside the horizon, escape remains possible. Inside it, every possible future path through space-time leads deeper inward. The reason isn't that gravity suddenly becomes infinite, it doesn't. Instead, space-time itself has become so distorted that all roads now lead toward the center. Crossing the event horizon is not like crossing a border, it's more like crossing a waterfall in a river. Once you're past it, there is no route back upstream. While your experience seems almost uneventful, distant observers witness something completely different. As you approach the event horizon, the light coming from you becomes increasingly redshifted. Its wavelength stretches, its energy decreases, you appear dimmer and dimmer, your motion seems slower and slower. To a distant observer, you never appear to actually cross the horizon. Instead, you seem frozen near it. Eventually, you fade from view altogether. Meanwhile, from your own perspective, you crossed the horizon long ago and continue falling inward. This is one of the strangest consequences of relativity. Both descriptions are valid, neither observer is wrong. Reality itself depends on where you are observing from. Now the journey becomes dangerous. Gravity doesn't simply pull, it stretches. The side of your body closer to the black hole experiences slightly stronger gravity than the side further away. These differences are called tidal forces. Near a stellar mass black hole, tidal forces become enormous. Your feet would be pulled more strongly than your head. Your body would stretch, your width would shrink. The process becomes increasingly violent. Eventually, molecules would be torn apart, then atoms, then the particles within those atoms. Physicists have a surprisingly informal name for this process: spaghettification. And near many black holes, it would be fatal long before you reach the center. Supermassive black holes are different. The black hole at the center of our galaxy contains millions of times the sun's mass. Some black holes contain billions of solar masses. Because these objects are so large, the tidal forces at the event horizon can actually be relatively weak. In theory, you could cross the event horizon of a supermassive black hole without being immediately torn apart. You might survive for minutes, hours, or even longer depending on the black hole's mass. For a while, you could continue making observations, you could continue falling, you could continue experiencing the universe, but eventually, tidal forces would grow stronger as you approach the interior. The outcome remains the same, only the timescale changes. Inside the event horizon, space-time behaves in a way that is difficult to visualize. Outside a black hole, you can choose whether to move north, south, east, west, up, or down. Inside the horizon, your options become increasingly restricted. According to general relativity, moving toward the center becomes as unavoidable as moving toward tomorrow. You cannot stop, you cannot turn around, you cannot hover. Every future-directed path leads inward. This is not because you lack sufficient rocket power. No conceivable rocket could change the outcome. The geometry of space-time itself is carrying you toward whatever lies ahead. According to classical general relativity, your journey ends at something called a singularity. A singularity is often described as a point where density becomes infinite and space-time curvature becomes infinite. But physicists treat this prediction with caution. Whenever infinities appear in physical equations, they usually indicate that a theory has reached the limits of its applicability. Most researchers do not believe nature literally contains infinities. Instead, many suspect that our current equations are incomplete. The singularity may not be a real physical object. It may be where general relativity breaks down and a deeper theory takes over. Unfortunately, we do not yet know what that deeper theory looks like. Black holes create another major problem for physics. According to standard quantum mechanics, information should never truly disappear. The complete quantum state of a system evolves in a way that preserves information. Black holes appear to challenge this principle. Imagine throwing a library into a black hole. Every page contains information. Every atom contains information. Now imagine the black hole eventually evaporating through Hawking radiation. Where does that information go? This question became known as the black hole information paradox. For decades, it has been one of the most important questions in theoretical physics. Many physicists now believe that information is somehow preserved, but exactly how that happens remains an active area of research. In 1974, Stephen Hawking discovered something remarkable. Black holes are not completely black. Quantum effects near the event horizon should cause black holes to emit tiny amounts of radiation. This process is now known as Hawking radiation. Over unimaginable periods of time, a black hole should slowly lose energy. Eventually, it should evaporate. A stellar mass black hole would take vastly longer than the current age of the universe to disappear. But the prediction has profound implications. It links gravity, quantum mechanics, and thermodynamics, and it raises a profound question. If black holes can evaporate, what ultimately happens to everything that fell inside? At present, nobody knows with certainty. And that uncertainty is one of the reasons black holes remain among the most important objects in modern physics. So, what happens inside a black hole? Surprisingly, we know much more than many people realize. We know that time slows in extreme gravity. We know that crossing the event horizon may feel completely uneventful. We know that tidal forces can stretch and destroy matter. We know that once the event horizon is crossed, escape becomes impossible. But beyond that, certainty begins to fade. The deepest interior of a black hole remains hidden behind a barrier the universe does not allow us to observe. Somewhere inside, general relativity and quantum mechanics stop agreeing with one another. And until a new theory unites them, the final stage of the journey remains unknown. Black holes are not simply cosmic objects, they are laboratories for the deepest questions in physics, and whatever truly happens inside them may eventually reveal an entirely new understanding of reality itself. We'll start relatively close to home. The sun may seem calm compared to the monsters we'll discuss later, but it is capable of unleashing staggering amounts of energy. Solar flares occur when twisted magnetic fields above the sun's surface suddenly snap and reconnect. In just minutes, they can release energy equivalent to billions of nuclear bombs. Often accompanying them are coronal mass ejections, enormous clouds of electrically charged plasma blasted into space at millions of kilometers per hour. Fortunately, Earth's magnetic field protects us from most of the damage. But powerful solar storms can disrupt satellites, communication systems, GPS networks, and electrical grids. Compared to what comes later, these events are relatively mild, but they remind us that even our own star is capable of cosmic violence. When a massive star reaches the end of its life, gravity finally wins. For millions of years, nuclear fusion pushes outward while gravity pulls inward. Eventually, the fuel runs out. The star's core collapses in a fraction of a second. Temperatures soar into the billions of degrees. Matter is crushed to incredible densities. Then the entire star explodes. A supernova can briefly outshine an entire galaxy. During the explosion, elements such as oxygen, silicon, calcium, and iron are blasted into space. The atoms in your body were forged in stars like these. In other words, every person on Earth is made from the debris of ancient stellar explosions. Violent as they are, supernovae are also creators. Without them, planets and life itself would never have existed. Imagine taking the mass of the Sun and compressing it into a sphere only about 20 kilometers across. That is a neutron star. Now give that neutron star the most powerful magnetic field known in the universe. You get a magnetar. A magnetar's magnetic field can be more than 1,000 times stronger than that of a typical neutron star, and trillions of times stronger than Earth's magnetic field. The magnetic stress can literally crack the star's crust. When that happens, the magnetar releases colossal bursts of X-rays and gamma rays. In 2023, astronomers observed a giant flare from a magnetar in the galaxy M82 that released an extraordinary amount of energy in just a fraction of a second. If a powerful magnetar flare occurred close enough to Earth, it could significantly affect our atmosphere and technology. Fortunately, no known magnetars pose that kind of threat. For decades, gamma-ray bursts puzzled astronomers. Today, we know they are among the most energetic explosions ever observed. Some occur when massive stars collapse into black holes. Others happen when neutron stars collide. For a few seconds, an immense beam of gamma radiation erupts into space at nearly the speed of light. If one of these narrow jets happens to point directly towards Earth, the burst appears unbelievably bright. In only seconds, a gamma-ray burst can release as much energy as our sun will emit during its entire lifetime. These explosions are so luminous that some have been detected from billions of light years away. They're essentially cosmic searchlights visible across much of the observable universe. Two neutron stars orbiting each other create one of the most violent dances in existence. As they circle, they emit gravitational waves and gradually spiral closer together. Eventually, they collide. The impact occurs at a significant fraction of the speed of light. Matter is compressed beyond anything achievable on Earth. A brilliant explosion known as a kilonova follows. These collisions are thought to create large quantities of heavy elements such as gold, platinum, and other rare metals. The famous 2017 event known as GW170817 allowed scientists to observe gravitational waves and light from the same cosmic catastrophe for the first time. It marked the beginning of a new era in astronomy. Imagine drifting too close to a supermassive black hole. The side of your body nearest the black hole would feel a stronger gravitational pull than the far side. The difference becomes so extreme that you would be stretched apart. This process is called tidal disruption. When it happens to a star, the result is known as a tidal disruption event. The star is literally shredded by gravity. Some of its material is flung outward. The rest spirals into the black hole, heating to enormous temperatures and producing a brilliant flare visible across vast cosmic distances. For a brief period, a single doomed star can outshine its host galaxy. When two black holes collide, something remarkable happens. There is no giant flash, no explosion visible to ordinary telescopes. Instead, the violence is carried away by gravitational waves. As the black holes spiral together, they warp space and time itself. At the moment of merger, enormous amounts of mass can be converted directly into energy. The first detection of a black hole merger in 2015 confirmed a major prediction of Einstein's theory of general relativity. Since then, hundreds of mergers have been detected by observatories such as LIGO, Virgo, and Kagra. These events rank among the most energetic phenomena ever measured. The difference is that much of their energy leaves as ripples in space-time rather than visible light. At the center of many galaxies lie supermassive black holes. Most are relatively quiet, some are not. When huge amounts of gas fall toward a supermassive black hole, an intensely hot accretion disk forms around it. The resulting object is called a quasar. Quasars can shine brighter than entire galaxies despite originating from a region smaller than our solar system. The energy does not come from fusion, it comes from gravity. Matter falling into the black hole releases enormous amounts of energy before crossing the event horizon. Some quasars were already blazing when the universe was less than 1 billion years old. Even today, they remain among the brightest objects ever discovered. Some active black holes do more than consume matter, they launch it. Magnetic fields near the black hole can accelerate particles into enormous jets traveling close to the speed of light. These jets can extend far beyond their host galaxies. In 2024, astronomers reported the largest known black hole jet system ever observed. Named Porphyrion, it stretches roughly 23 million light-years across. To put that into perspective, that's around 140 times the diameter of the Milky Way. These structures can influence the evolution of entire galaxies and galaxy clusters. They are among the largest and most powerful engines in the known universe. At number 1, we arrive at perhaps the most intimidating cosmic phenomenon currently known. A blazar is a special type of active supermassive black hole. Like other active galaxies, it launches powerful jets. The difference is orientation. One of the jets happens to be aimed almost directly at Earth. Because of relativistic events, the jet appears dramatically brighter than it otherwise would. The result is an object capable of producing staggering amounts of observable energy. Blazars are suspected of accelerating particles to energies far beyond anything achievable by human technology. Recent research investigating the highest energy neutrinos ever detected points towards blazars as potential sources. They are effectively cosmic particle accelerators operating on scales that defy imagination. And when one points in our direction, we witness some of the most extreme physics in the universe. The universe doesn't do things by halves. Stars explode, neutron stars collide, black holes devour suns, merge with each other and launch jets that span millions of light years. And despite everything we've covered today, these are only the phenomena we've discovered so far. Every year, new observatories reveal events more powerful, stranger, and more extreme than we thought possible. The truth is that the universe isn't a quiet collection of stars. It's an arena of constant creation and destruction, governed by forces so immense that our everyday experience barely prepares us to comprehend them. And somewhere, right now, one of these violent cosmic events is unfolding. The light just hasn't reached us yet. Thank you for watching this video. I hope you enjoyed the Phase 1 marathon. Let me know what you think of the first phase down in the comments. Make sure you hit the subscribe button, and if you have anything you would like to explore with me in a future video, I will do my best to make that happen. Stay tuned for the next video of Phase 2, where we explore more of the strangest planets in the universe, and as always, stay curious.